Three of the largest diesel locomotives on Earth are built, run for barely 6 years, and are cut up for scrap. No museum piece, no preservation, no survivors. The photographs are nearly all that's left. This is the ALCO Century 855, 86 feet long, roughly 550,000 pounds. Two 16-cylinder prime movers in one car body, 16 axles, and 5,500 horsepower. It was the largest diesel locomotive ALCO ever produced, though not the largest ever produced. That record went to EMD's DDA-40X, which served for decades and survives in museums today. ALCO's machine vanished entirely, and what killed it tells a much bigger story than one failed locomotive. In June 1964, Union Pacific accepted delivery of the Century 855 fleet, a specialized order of just 3 units numbered 60, 61, and the cableless booster 60B. This was ALCO's ultimate engineering statement, the absolute physical limit of its catalog, designed to prove that the Schenectady builder could still dominate the high-horsepower race. While Electromotive's later designs would ultimately claim the all-time industry records for length and power, this 3-unit anomaly represented ALCO's boldest bid to capture the transcontinental market. Union Pacific wanted to compress massive tractive effort into fewer car bodies, pushing both builders and mechanical departments to the edge of what was practical. Yet instead of a new fleet standard, the experiment ended in a rapid withdrawal from service, leaving historians with only scattered photographs and paper records to reconstruct what went wrong. The question remains, was this extreme build a flawed design, or a victim of a collapsing corporate empire? The sheer physical presence of the Century 855 reflected the extremes of 1960s locomotive design. Stretching 86 feet over coupler faces, this massive machine was the largest locomotive ALCO would ever construct. On its own, a single unit weighed roughly 528,000 pounds when fully provisioned, concentrated onto a massive steel frame. To distribute this immense weight and protect the rails, the design utilized 16 axles, carried by 4 two-axle trucks, linked by heavy span bolsters, components salvaged directly from Union Pacific's retired gas turbine fleet. Inside the single car body sat 2 independent power plants, rather than one. ALCO installed a pair of its new 16-cylinder 251C prime movers, each rated at 2,750 horsepower. Combined, they delivered a total of 5,500 horsepower to 8 General Electric 752 traction motors. While Electromotive's later DDA-40X would eventually eclipse these figures, reaching 98 feet in length and 6,600 horsepower to become the largest diesel locomotive ever built. The C855 was, for its moment, an unrivaled giant in ALCO's catalog. Every component had to be carefully packaged to fit this dual-engine configuration. The single frame held not only the 2 V16 engines, but also 2 GT598 main generators, massive fuel tanks carrying up to 6,000 gallons, and a complex central radiator bank designed to cool both prime movers simultaneously. This dense concentration of mechanical and electrical systems created an incredibly heavy, complex machine. It was a configuration that promised unprecedented pulling power, but also placed an extraordinary amount of physical and thermal stress on a single, rigid frame. Union Pacific's overland route faced its most grueling physical obstacle on Sherman Hill in Wyoming. This 65-mile stretch of track rose from Cheyenne to a summit of over 8,000 feet, presenting a sustained 1.14% grade that dictated the economics of the entire railroad. Hauling massive freight trains over this summit demanded immense tractive effort. For years, the railroad relied on its unique fleet of gas turbine electric locomotives to supply the necessary brute force. While these turbines successfully moved heavy tonnage, they did so at a steep economic cost. They consumed immense amounts of heavy bunker sea oil fuel and required highly specialized, expensive maintenance. As the first-generation gas turbines aged in the early 1960s, Union Pacific needed a practical diesel-powered replacement that could match their concentrated horsepower without the accompanying financial penalties. Older diesel setups of the era could not easily solve this problem. To move a heavy freight train over the pass using standard locomotives required as many as 10 separate units coupled together. This configuration created a maintenance and operational nightmare. Each additional locomotive added another cab to inspect, more electrical connections to fail, and more diesel engines to maintain, all while requiring larger crews and frequent shop visits. To resolve this issue, Union Pacific's Chief Mechanical Officer, D.S. Newhart, launched an ambitious unit reduction program in 1963. Newhart sought to radically compress the railroad's locomotive fleet. His target was a single, cohesive consist capable of delivering 15,000 horsepower, but composed of only 3 highly concentrated twin-engine units. This setup would slash the number of cabs, simplify train handling, and significantly reduce maintenance events. It was a bold operating directive that turned a severe geographic hurdle into a direct procurement challenge, forcing the nation's remaining locomotive builders to compete on raw, concentrated horsepower. Historically, the American Locomotive Company was an industrial giant, standing for decades as the second-largest locomotive builder in the nation. But the rapid transition to diesel power after World War II shattered that secure footing. By the mid-1950s, General Motors' Electromotive Division, or EMD, captured roughly 85% of all domestic diesel sales. EMD built its empire on standardization, turning out highly dependable mass-produced locomotives that railroad mechanics trusted, leaving rivals struggling to keep pace. ALCO's difficulties multiplied when its critical partnership with General Electric dissolved in 1953. For decades, GE had supplied the heavy electrical generators and traction motors that powered ALCO's diesel engines. The end of this alliance did more than disrupt production. It transformed a key partner into a direct, powerful competitor. GE soon entered the domestic locomotive market with its own road switcher, the U-25B, rapidly securing a foothold among major railroads. By the early 1960s, ALCO was caught in a tightening vice, squeezed between EMD's massive market dominance and GE's aggressive rise. The Schenectady builder watched its market share bleed away year after year. To survive, the company had to prove it could still compete in the high-horsepower race. Union Pacific's unit reduction program represented the perfect opportunity to strike back. Winning this order was not just about building 3 experimental units. It was a high-stakes gamble to demonstrate that ALCO still belonged at the forefront of heavy railroading. In 1963, Chief Mechanical Officer D.S. Newhart formalized his vision, sending a competitive solicitation to the nation's 3 remaining locomotive builders. Union Pacific challenged Electromotive, General Electric, and ALCO to design a dual-engine locomotive capable of meeting the railroad's demanding 15,000 horsepower threshold in a 3-unit consist. Each manufacturer responded with its own interpretation of the concentrated power brief, setting off a direct corporate rivalry. For ALCO, the response was the Century 855. To fulfill Union Pacific's operational plan, the order was split into a precise 3-unit configuration. ALCO constructed 2 cab-equipped lead units, designated road numbers 60 and 61, designed to control the train and house the crew. Sandwiched between them was road number 60B, a cabless booster unit. Together, they formed a highly specialized ABA arrangement spanning nearly 260 feet of track. The booster unit was entirely dependent on its partners. It contained no operating controls of its own and was operated remotely from either lead cab through a complex network of multi-unit cables. This 3-unit set was never intended to be a standardized production fleet right out of the gate. Union Pacific treated the order strictly as a demonstration run, a high-stakes experiment to evaluate whether this massive twin-engine concept could survive the brutal operating realities of transcontinental freight service. It was a calculated, highly limited bet. If these 3 units succeeded on the grueling grades of Sherman Hill, a massive production contract would follow. But for ALCO, there was no room for error. These demonstration units had to perform flawlessly from their very first run, proving their reliability before the railroad would commit to a full fleet. ALCO did not design a brand new, unproven prime mover to meet Union Pacific's high horsepower challenge. Instead, they relied on the 251 engine family, a rugged and successful medium-speed diesel design that had powered their locomotives for years. For the C855, ALCO took 2 of these proven 2,750 horsepower 251C prime movers, along with their matching main generators, and packaged them onto a single, massive steel frame. Beneath this heavy frame, the design utilized 4 axle assemblies linked by span bolsters. These heavy structural components were salvaged directly from Union Pacific's retired gas turbine locomotives, providing a rugged, pre-existing foundation. Individually, every major piece of the C855 had an established precedent. The 251 engine was a known quantity, the heavy electrical gear was proven, and the trucks had already run thousands of miles. The true engineering challenge lay in the packaging itself. Combining these massive, independent systems into a single, cohesive locomotive created an entirely new task of system-level integration. Success would depend on how well these separate components functioned as a unified whole, testing whether ALCO's engineering team could successfully manage the transition from building individual components to delivering a complex, highly integrated dual-engine package. After accepting the 3 experimental units in June 1964, Union Pacific quietly halted further procurement. The expected follow-up contract never materialized, leaving the Century 855 roster permanently frozen at just 2 cab units and a single booster. This sudden hesitation was not isolated to ALCO's design, as competing builders also struggled to make the dual-engine concept work reliably. Across the railroad industry, the entire concept of the high-horsepower, double-engine locomotive was showing its limits. During this same period, Union Pacific was also testing Electromotive's DD35 family and General Electric's U50. These twin-engine competitors faced their own steep hurdles, from complex control synchronization to high-maintenance demands. As the mid-1960s progressed, railroad executives began to question whether consolidating immense horsepower into fewer, giant car bodies was truly more efficient than running traditional fleets of standard single-engine units. The promise of headline-grabbing horsepower did not guarantee everyday reliability. The operational struggles of the DD35 and U50 suggested that the difficulties of twin-engine standardization were industry-wide, extending far outside the engineering capabilities of any single builder. For Union Pacific, the massive 3-unit ALCO set was no longer the vanguard of a new fleet. It was an isolated, highly expensive experiment. To find out why the railroad refused to order more, the focus turned directly to the C855's actual performance in daily freight service. Operating 2 independent 2,750 horsepower prime movers on a single chassis introduced immediate mechanical complications. Instead of a single point of failure, the Century 855 duplicated every major operating system. The massive locomotive carried 2 engines, 2 turbochargers, 2 governors, and 2 GT598 main generators. In the grueling environment of Sherman Hill, these dual power plants ran at maximum output for hours at a time, generating immense thermal energy. The central radiator bank, positioned between the engine compartments, struggled to dissipate this concentrated heat. As temperatures spiked on steep Wyoming grades, the cooling system repeatedly failed to keep pace. This caused coolant temperatures to exceed safe operational limits, triggering automatic protective shutdowns of the prime movers to prevent catastrophic engine failure. Managing the electrical output of both generators added another layer of instability. The 2 GT598 generators fed a common electrical bus to power the traction motors. To make this setup work, The control circuits had to constantly balance and synchronize the speed and voltage of both diesel engines. Because of the complex control wiring, the system struggled to maintain this precise balance. If one engine experienced a power drop, the electrical mismatch frequently tripped protective relays. This caused both engines to shut down simultaneously. While a twin-engine design theoretically offered operational redundancy, the reality in daily service was the opposite. The control systems did not allow for simple single-engine operation if one plant failed. If a single generator or prime mover suffered a fault, the entire locomotive, weighing 528,000 pounds, became dead weight. Without extensive manual rewiring in the field, a failure on one side of the frame crippled the entire unit, requiring a helper locomotive to rescue the train from the main line. Mechanical wear was further accelerated by physical forces within the frame. Running two massive V16 engines in close physical proximity created severe harmonic vibrations at specific engine speeds. These constant vibrations weakened frame joints and caused premature wear on the traction motor-bearing housings. With cooling failures, electrical faults, and vibration damage constantly sidelining the units, the C855 fleet suffered from exceptionally low operational availability. This frequent downtime erased the economic advantage of concentrated horsepower, proving that raw tractive effort meant little if the locomotive could not reliably leave the yard. With only 3 C855 locomotives on the Union Pacific roster, the railroad's mechanical department faced an immediate economic obstacle. Modern railroads run on standardization. The massive shops at North Platte, Nebraska, were organized to service standard electromotive F units and GP series locomotives. Standard units meant standardized parts, predictable maintenance steps, and interchangeable components. The C855 shared almost nothing with these fleets. Because only 3 units existed, numbers 60, 61, and 60B, every repair became a custom engineering project. The shop lacked the specialized overhead clearances, lifting jigs, and heavy tooling required to easily pull the twin 251C engines or access the dual main generators. Union Pacific's mechanics had to fabricate custom shop tooling on a limited budget just to perform routine overhauls. This specialized labor and non-standard layout added roughly 30% more maintenance hours to every shop visit. Logistically, the parts supply chain was non-existent. For a fleet of 3, Union Pacific's parts department could not justify stocking a dedicated inventory of specialized C855 components, dual generator control modules, or salvaged turbine span bolsters. Every replacement part required a special order from ALCO's Schenectady plant. But by the mid-1960s, ALCO's service network was rapidly deteriorating, causing lead times for critical components to stretch into weeks. An internal Union Pacific cost analysis in 1966 estimated that maintaining a single C855 cost approximately $150,000 annually. This was roughly double the cost of an EMDDD-35A of similar power. The unit reduction program had promised massive operational savings, but those savings were completely devoured on the shop floor. ALCO's declining corporate support left Union Pacific with a trio of high-maintenance orphans, turning the ultimate high-horsepower experiment into a logistical trap. Railroad operations are inherently unpredictable. A freight train climbing a mountain pass requires immense tractive effort, but once it reaches flat territory, that extreme power becomes dead weight. Tonnage, grades, and shifting traffic patterns mean that power requirements change constantly from one division to the next. With standard separate locomotives, a railroad can scale its power to match these shifting demands. Operators can add, remove, or reassign individual units as conditions change along the route. If one locomotive in a multi-unit set experiences a mechanical issue, crew members can isolate that specific unit on the fly. The remaining engines continue pulling the train, keeping the main line open and traffic on schedule. A single giant machine completely upends this operational flexibility. By concentrating 5,000 horsepower or more into one frame, a railroad ties its entire train to a single mechanical asset. A failure in one engine, one cooling fan, or one electrical cabinet can render the entire unit useless. Instead of isolating a single engine and moving on, a failure forces the railroad to halt the train, dispatch a rescue locomotive, and tow the massive dead machine back to the yard. This operational vulnerability drove an industry-wide preference for fleet commonality over prestige locomotives. Standardized units simplified every level of railroading. Engineers and shop crews only had to learn one control layout and mechanical architecture. Supply chains became efficient because purchasing departments stocked one set of standard parts, while maintenance shops established predictable, repetitive repair schedules. This standard approach turned locomotive fleets into modular networks. Ultimately, modularity defeated sheer mass as the industry's guiding operating principle. Railroads discovered that a pool of dependable, interchangeable units working in unison offered far more operational flexibility and economic utility than any single colossal machine could ever deliver. The true test of the giant twin-engine concept came 5 years after the Century 855 entered service. In 1969, Union Pacific introduced the Electromotive Division DDA-40X, a locomotive that proved physical scale and dual-engine architecture were not fundamentally flawed. Stretching 98 feet over coupler faces, the DDA-40X was 12 feet longer than ALCO's Giant and remains the longest diesel locomotive ever constructed. It delivered 6,600 horsepower from two 16-cylinder EMD 645E3A prime movers, establishing it as the definitive size and power record holder. Union Pacific and EMD records verify a total production run of 47 units built between 1969 and 1971. Unlike its troubled predecessors, the DDA-40X achieved a long, productive career on the overland route, remaining in active freight service into the mid-1990s. 13 of these massive machines survive today in museums across the country, with one unit retained in Union Pacific's active heritage fleet. The contrast in longevity reveals that execution and manufacturer support, rather than size alone, determined the viability of the twin-engine design. EMD built the DDA-40X using its mature 645 engine platform, a highly dependable prime mover that railroad mechanics already understood. While ALCO struggled to integrate disparate electrical systems and older truck designs under the C855, EMD engineered a cohesive, unified system designed for heavy mainline operations. Because the DDA-40X shared power assemblies, valves, and electrical components with hundreds of standard EMD locomotives in the Union Pacific fleet, parts were readily available in every major terminal. EMD backed its locomotives with a nationwide parts depot network and on-site technical field representatives. The 47-unit fleet created an economy of scale that justified dedicated maintenance training and custom shop tooling at North Platte. EMD's massive market share and financial stability meant that when mechanical issues arose, the builder had the engineering depth to redesign components and distribute field modifications quickly. The DDA-40X demonstrated that a double diesel locomotive could succeed in daily service, provided it had the backing of a dominant manufacturer. The giant twin-engine concept was workable, but it required the backing of a manufacturer with the industrial scale and financial strength that ALCO no longer possessed. In 1969, as the final DDA-40X units were entering production, the American Locomotive Company closed its historic Schenectady plant, marking ALCO's official exit from the North American locomotive business. The Century 855, built just 5 years prior, stood as the largest machine the builder ever constructed, completed virtually at the finish line of its corporate existence. For Union Pacific, the three-unit experiment quickly reached its terminal point. The railroad formally withdrew numbers 60, 61, and 60B from active service in August 1970, relegating them to storage after only 6 years of intermittent mainline duty. The physical dissolution of the locomotives followed shortly after. In September 1971, Union Pacific sold the stored trio to an industrial maintenance firm, which transferred them to Houston Armature Works in Texas for scrapping. Dismantling began in December 1971 with the cableless booster, 60B. Unit 61 was cut up in January 1972, followed by the final lead unit, number 60, in February. By the spring of 1972, the largest locomotives ALCO ever built had been completely reduced to scrap metal, leaving no physical survivors of its ultimate high-horsepower gamble. The American Locomotive Company was already failing long before the swift demise of the Century 855. The builder's decline had been compounding for decades, long before the first twin-engine frame was welded in Schenectady. By the mid-1960s, ALCO had lost the war that truly mattered, the unglamorous battle of customer support, parts availability, and fleet dependability. While Electromotive secured its dominant market share by perfecting a highly responsive field service model, ALCO repeatedly focused on winning the high-horsepower race on paper. Headline-grabbing specification sheets could not buy back the confidence of railroad mechanical officers who watched non-standard locomotives sit idle for weeks waiting for custom parts. This strategic mismatch exposed a deeper failure in how ALCO allocated its dwindling capital. Instead of investing in a nationwide parts distribution network or stabilizing its core diesel engines, the company committed scarce resources to complex, low-volume prestige projects. A fleet of only 3 highly specialized units like the Century 855 could never generate the economies of scale needed to justify its own maintenance infrastructure. Every custom component ordered from a shrinking supplier base highlighted a service network in terminal decay. The Century 855 was a visible symptom of corporate collapse. It stood as a monument to a company that chased engineering prestige, while the structural foundations of its business crumbled. Ultimately, the giant locomotive remains a classic example of the right machine offered by the wrong company at the worst possible moment. When Schenectady finally closed its doors in 1969, it was the result of cumulative competitive pressures and strategic missteps that had slowly starved the enterprise of its market share. The massive experiment was simply the final, ambitious roll of the dice from a builder that had already run out of time. The twin-engine heavy-haul concept was technically plausible in principle. Concentrating massive tractive power into a single frame addressed a genuine operational need for railroads seeking to reduce fleet sizes. Yet the physical execution of the Century 855 and the heavy maintenance burden it placed on shops must be evaluated apart from the underlying concept. Did the locomotive fail because the double diesel design was fundamentally unworkable, or because the manufacturer lacked the industrial scale and service network to support it? Corporate timing and ALCO's terminal decline cannot be easily separated from a simple design verdict. Perhaps this giant machine was not a structural failure, but the right mechanical solution offered by the wrong company at the wrong moment. The answer remains unresolved, a subject of ongoing debate for historians and railroaders alike. Today, the tracks of Sherman Hill are dominated by standardized, modular fleets. The ultimate lesson of the Century 855 isn't about physical scale, but corporate survival. It proves that even the most ambitious engineering fails without a foundation of service and support. Was it a flawed giant? Or simply the right machine at the worst possible moment? Share your thoughts in the comments below.